Welcome to a new section, focusing on more advanced and functional programming features in Python. We start with Lambda functions. A Lambda function is a small, anonymous function defined in a single line. They are often called anonymous because they don't have a formal name like functions defined with the def keyword. 1. Standard function versus Lambda function. Compare a standard def function, like add_10, to its Lambda equivalent. A standard function requires the def keyword, a name, parentheses for arguments, the return keyword, and a block of indented code. A Lambda function uses the Lambda keyword, followed by arguments, a colon, and the single expression to be returned. 2. The Lambda syntax and structure. The syntax is simply the Lambda keyword, followed by one or more arguments, separated by commas, a colon, and a single expression. The value of this expression is automatically returned, so you don't need the return keyword. 3. Assigning and calling a Lambda. You can assign the Lambda function object to a variable like my_Lambda. Then you call the variable name with arguments just like a normal function. However, the primary use case for Lambdas is passing them directly as arguments to higher-order functions like map and filter, which maybe we'll see soon. 4. Key limitations. Lambdas are limited to a single expression. You cannot include multiple statements, complex control flow like if-else blocks, or multiple lines of code. They are suited for simple, quick, one-off operations. To summarize, Lambda functions provide a clean, concise way to define simple operations without formal function definitions. We will see their true power when we use them to streamline sorting and filtering operations. Our next lecture 13.02. Lambda, cube of a given number. See you there. Welcome back. Let's start practicing Lambda functions by creating a simple anonymous function that calculates the cube of any given number. This exercise will reinforce the core Lambda syntax. 1. Defining the Lambda function. We assign our Lambda to a variable called cube. The structure is Lambda, followed by one argument, x, a colon, and the expression, which is x raised to the power of 3. Remember, the result of the expression is automatically returned. 2. Executing the Lambda. We can now execute the Lambda function by calling the variable name, cube, and passing in an argument. When we pass 5, it returns 125. When we pass 2, it returns 8. The syntax is clean and concise for this simple mathematical operation. 3. Comparison with standard function. Notice how much code the Lambda function saves compared to the traditional def function for the exact same logic. For simple, one-off operations, the Lambda function is the preferred, idiomatic Python approach. To summarize, we created a simple, single-argument Lambda. The Lambda keyword, followed by the argument and the expression, provides instant functionality without the boilerplate of a full function definition. Our next lecture 13.03. Lambda, even or odd. See you there. Welcome back. While Lambda functions are limited to a single expression, we can still perform simple conditional logic inside them using the ternary operator or the conditional expression. This allows us to check if a number is even or odd and return a corresponding string, all in one line. 1. The ternary operator syntax. This operator is Python's way of writing an if-else statement as a single expression, which is what a lambda function requires. The structure is the value to return if the condition is true, followed by the if keyword, the condition itself, the else keyword, and finally, the value to return if the condition is false. 2. Defining the even or odd lambda. We define check_parity. It takes one argument, number. The expression uses the ternary operator. If number modulus 2 equals 0, it returns even. Otherwise, it returns odd. This entire logic fits neatly into the single lambda expression. 3. Testing the lambda. When we call check_parity with 4, the condition is true, and it returns even. When we call it with 7, the condition is false, and it returns odd. This demonstrates how to pack conditional logic into the lambda's single expression limit. To summarize, when you need a lambda to return one of two values based on a simple test, you may use the ternary operator for the job. It maintains the lambda's conciseness while providing necessary logic. Okay, our next lecture 13.04. Lambda, sum of two numbers. See you there. Welcome back. While our previous lambdas only took one argument, a lambda function can handle any number of arguments. In this short exercise, we will define a lambda that takes two parameters and returns their sum, demonstrating the multi-argument syntax. 1. Defining the multi-argument lambda. We name our lambda sum_2. The arguments a and b are separated by a comma before the colon. The expression is simply a plus b. This structure shows that the argument side of the lambda is just a list of parameters, similar to a regular function's parentheses. 2. Executing the lambda. We call sum_2 with two arguments, 10 and 5, which are correctly mapped to a and b based on their position. The function returns 15. In the second example, 120 return 120. This confirms that the lambda correctly handles multiple positional arguments. 3. Lambdas and dynamic typing. Since lambdas are functions, they also follow Python's dynamic typing. The same addition operator works differently when used with strings, performing concatenation instead of arithmetic addition. This means one lambda can serve multiple data types. To summarize, lambdas are versatile. They can take one, two, or many arguments, as long as the entire logic remains a single, returnable expression. Our next lecture 13.05. Using a filter. See you there. Welcome back. We now explore the primary use case for Lambda functions, using them anonymously with Python's built-in higher-order functions. We start with the filter function, which allows you to select elements from an iterable that satisfy a specific condition. 1. Understanding the filter function. The filter function takes two arguments, a function and an iterable like a list. The function must return a Boolean value, true or false. Filter applies this function to every item in the iterable and only keeps the items for which the function returns true. The result is a filter object, which we typically convert to a list. 2. Filtering even numbers with Lambda. Here is our list of numbers. We pass our anonymous Lambda directly as the first argument to filter. The Lambda checks if a number is divisible by 2. Filter then processes the numbers list and even underscore filter, only retains the elements where the lambda returned true. Finally, we convert the result to a list, showing only the even numbers. 3. The benefit of using lambda. If we had used a regular def function, we would have needed 4 lines of code just to define a simple is_even function. By using an anonymous lambda, we define the filtering condition right where we need it, keeping the code clean, concise, and localized to a single line. To summarize, combining filter with a lambda is idiomatic Python for filtering data. The lambda provides the Boolean logic, and filter handles the iteration. Okay, our next lecture 13.06. Using the map function. See you there. Welcome back. After learning about filter, we now turn to the map function. While filter is used for selecting elements, map is used for transforming or applying an operation to every element in an iterable. This is another core application for our concise lambda functions. 1. Understanding the map function. Like filter, map takes a function and an iterable. However, instead of checking for true or false, map applies the function to every single item and collects the result of that application. The output is a map object, which we typically convert to a list or another collection. 2. Squaring numbers with lambda and map. Here is our list of numbers. We pass an anonymous lambda that returns the square of the input, x. The map function applies this squaring operation to every number in the list. The squared_map object stores these results, and converting it to a list shows the new, transformed list: 1, 4, 9, 16, and 25. 3. Transforming strings. The lambda and map combination isn't just for numbers. Here, we use map to transform a list of lowercase names into uppercase names. The lambda simply calls the upper string method on each name, demonstrating its versatility for applying any single transformation. To summarize, use map and lambda when you want to change every item in a collection in the same way. It's concise, readable, and often more efficient than writing a traditional for loop. Okay, our next lecture 13.07. Using reduce function. See you there. Welcome back. We've learned filter for selection and map for transformation. Now, we introduce the last of the functional trio, the reduce function. The reduce function applies a function cumulatively to the items of an iterable, reducing the iterable to a single, final value. Unlike filter and map, reduce is not built in and must be imported. 1. Importing and understanding reduce. First, we must import reduce from the functools module. Reduce takes a function which must accept 2 arguments, an iterable and an optional initializer. It takes the first 2 items of the iterable and applies the function, then takes the result and the next item, and so on, until only one value remains. 2. Calculating the product with lambda and reduce. Here, our lambda is named product_lambda. It takes 2 arguments, ACC for accumulator or running result, and item for the current list item. It returns their product. Reduce applies this lambda cumulatively. It calculates 1 times 2, then takes the result, 2, and multiplies it by 3, then takes 6 and multiplies it by 4, resulting in the final product of 24. 3. The internal flow of reduce. Think of reduce as constantly combining the next element of the list with the accumulated result so far. This makes it ideal for aggregation operations like summation, finding the maximum value, or, as we did, calculating the product of all elements. To summarize, reduce is used for combining a list of things into one thing. The lambda must take two arguments for the current accumulation and the next item. With filter, map, and reduce, you have the core functional tools. Okay, our next lecture 13.08, Decorators. See you there. Welcome to an advanced Python topic, Decorators. Decorators are a key feature used heavily in web frameworks and library code. Simply put, a decorator is a function that takes another function as input, adds some functionality to it, and returns the augmented function, all without explicitly modifying the original function's code. 1. What is a decorator? A decorator is essentially a wrapper. Think of it like adding icing to a cake. The cake, the original function, remains fundamentally the same, but the icing, the decorator, adds new presentation or flavor, which is new functionality like logging, timing, or access control. It follows the pattern. Function A decorates function B. 2. Prerequisites. Nested functions. Decorators rely on two concepts we've already covered: functions inside another function and returning a function. Here, inner_func is defined inside outer_func, and outer_func returns inner_func. Decorators are built upon this exact pattern. The variable f now holds a reference to inner_func. Calling f executes the inner function, demonstrating how a function can be dynamically generated and returned. 3. The decorator mechanism. At a high level, a decorator, let's call it decorator, is simply a function that takes an original_func and returns a decorated_func. This decorated function contains the original function plus the extra logic added by the decorator. The returned function completely replaces the original function reference. To summarize, decorators provide a clean, reusable way to wrap functions and add common functionality without polluting the function itself. Okay, our next lecture 13.09, Decorator that doubles the result of a function. See you there. Welcome back. In this lecture, we will build a functional decorator. This decorator, called double_result, will take any function that returns a number and ensure that number is multiplied by 2 before being returned to the caller. This requires 3 layers of nested functions. 1. Defining the decorator structure. Our decorator, double_result, must take one argument, the function it is decorating, referred to as func. Inside, we define the wrapper function. This wrapper uses *args and *quargs to ensure it can accept any arguments intended for the original func. Finally, the decorator returns the wrapper function. 2. Adding the core logic. Inside the wrapper, we call the original func, forwarding all the collected *args and *quargs to it. The result is stored in original_result. Our decorator's unique logic is applied next. We multiply this result by 2 and return the modified value. The caller of the decorated function will now only see this doubled result. 3. Manual decoration and calling. We define a simple add function. To manually decorate it, we pass add to double_result. This returns the wrapper, which we assign back to decorated_add. When we call decorated_add with 3 and 2, the add function returns 5, but the wrapper intercepts this, multiplies 5 by 2, and returns 10. To summarize, we created a decorator that wraps and modifies the output of a target function. This manual method is important for understanding the mechanics. However, Python provides a much cleaner, more elegant way to apply this decoration, which maybe we'll see soon. Okay, our next lecture 13.10. Using Decorator. See you there. Welcome back. In the previous lecture, we built our double_result decorator and applied it manually. That manual assignment is how decorators fundamentally work, but Python provides a cleaner, more readable way to apply them using the @sign or @symbol syntax. 1. Reviewing the manual decoration. Recall that manually applying the decorator requires us to overwrite the original function reference. This is valid Python, but it requires an extra line of code and is less intuitive to read. 2. The @decorator syntax. The @sign syntax is a piece of syntactic sugar. Placing followed by the decorator's name, double_result, directly above the DEF line is exactly equivalent to the manual assignment. The function add is automatically passed to the double_result function, and the returned wrapper function replaces add. 3. Testing the decorated function. When we call add with 3 and 2, it is no longer the original add function. It is the wrapper returned by double_result. This wrapper calls the original add, gets 5, multiplies it by 2, and returns 10. The syntax makes the code extremely clear about what decorator is being applied. To summarize, the syntax is the standard and most Pythonic way to apply decorators. It is concise and visually shows the function's extra behavior. Okay, our next lecture 13.11. Decorating strings. See you there. Welcome back. We've seen decorators modify numbers. Now, let's build a decorator that adds some flair to string outputs. We will create a decorator that wraps the result of any function with a specific character, like asterisks, which is useful for formatting output messages. 1. Defining the star wrapper decorator. We define our decorator, star_wrapper, which takes the function func as input. The inner wrapper calls func, passing all arguments via *args and *quargs, and stores the string result. The decorator's logic then takes the result and prepends and appends 3 asterisks, modifying the string before returning it. 2. Decorating and calling the string function. We use the syntax to apply star_wrapper to get_greeting. When we call get_greeting with Alice, the original function returns hello, Alice, but the decorator wraps it in asterisks, returning **hello, Alice***. This clearly shows that the decorator works seamlessly with string outputs. 3. The flexibility of decorators. This example highlights how versatile decorators are. Whether the function returns a number, as in the previous lecture, or a string, the decorator can add functionality, such as modifying the return value, timing the execution, or adding authentication, without altering the function's internal logic. To summarize, we use the decorator pattern and the at syntax to add structural modification to a string result. Since a function is just an object, we can apply as many decorators as we want to it. Okay, our next lecture 13.12. Decorator Chaining. See you there. Welcome back. Now that we can apply a single decorator using the @ sign syntax, let's explore decorator chaining. This is the process of applying multiple decorators to a single function to combine their functionalities. This is very common in frameworks like Django and Flask for tasks like logging and authentication. 1. Defining multiple decorators. We will reuse our two previous decorators, double_result, which multiplies the output by 2, and *_wrapper, which converts the output to a string and wraps it in asterisks. Notice that *_wrapper now uses str to handle the numerical output from the first decorator. 2. Applying the decorators. To apply multiple decorators, you simply stack the @ syntax lines one after the other, directly above the function definition. Here, we apply *_wrapper on top of double_result, which decorates the calculate function. 3. The execution order. When chaining, the decorators are applied bottom-up, meaning the one closest to the function, double_result, is applied first. This result is then passed to the next decorator up, *_wrapper. The execution order is: calculate runs first, then double_result modifies the output, and finally, *_wrapper modifies that output one last time before the final result is returned to the user. To summarize, decorator chaining allows for modular function enhancement. The order matters significantly because the output of one decorator becomes the input of the next. This completes our section on decorators. Okay, our next lecture 13.13. Generators. See you there. Welcome to the section on generators. Generators are a powerful and memory-efficient way to create iterators in Python. Unlike regular functions that return a single result and then terminate, generators can pause their execution, yield a value, and then resume exactly where they left off when the next value is requested. 1. The problem: memory usage. Consider a regular function that creates a large list. When you call create_list with 1,000,000 items, the entire list of 1,000,000 numbers must be created and stored in your computer's memory immediately before the function can return. This uses a lot of memory, which can crash your program if the list is too big. 2. The solution: the yield keyword. Generators solve this problem by replacing the return keyword with yield. When a function contains yield, it becomes a generator function. The yield keyword doesn't stop the function completely. It pauses it, sends a value back, and saves its internal state. The function can then be resumed from where it paused. 3. Lazy evaluation. This pausing and resuming is called lazy evaluation or on-demand generation. The generator only calculates and gives you the next value when you explicitly ask for it, typically by iterating over it in a for loop. This means that even a generator capable of producing 1,000,000,000 numbers will only hold one number in memory at any given time, making it incredibly memory efficient. To summarize, generators are essential for handling large datasets or infinite sequences without running out of memory. The presence of the yield keyword is the defining feature of a generator function. Okay, next lecture 13.14. Create a generator. See you there. Welcome back. Let's get hands-on and create a simple, practical generator function. We will build a generator that produces a sequence of even numbers up to a specified limit. This example will demonstrate the behavior of the yield keyword and the lazy evaluation process. 1. Defining the generator function. We define even_number_generator, which takes a limit n. Inside, a for loop iterates up to n. The key is the yield keyword inside the if condition. When this line is reached, the function pauses, returns the current even number, and waits until the next value is requested. 2. Creating the generator object. When we call the function even_number_generator with 10 and assign the result to gen, the code inside the function doesn't execute immediately. Instead, it returns a special object, a generator object. This object is an iterator that controls the function's pause state. 3. Iterating and executing the generator. We can manually pull values out using next. The first next call runs the code until the first yield, returning 0. The second next call resumes the function exactly after the first yield, continues the loop, finds the next even number, 2, yields it, and pauses again. Most of the time, we simply iterate over the generator object using a for loop which automatically handles all the next calls. To summarize, generators are memory superheroes. They generate large sequences on demand, keeping your code efficient. Our next lecture 13.15. Keywords in Python. See you there. Welcome to our final lecture in this section. Since we have learned many advanced topics like Lambda functions, decorators, and generators, let's take a moment to review the fundamental reserved words, the keywords in Python. You cannot use any of these keywords as variable or function names. 1. Basic control flow and data structure keywords. These are the words you've used most often. If, else, and elif manage branching logic. For and while manage loops with break and continue, modifying loop execution. Return exits a function and in, is, not, and, or, are for membership testing and logical operations. Maybe this keyword is the keyword, you will not often use it. 2. Function and object keywords. This group includes the foundation of object-oriented programming, def for functions, class for defining custom types, and self for instance methods. We also have the keywords we just covered, Lambda for anonymous functions and yield for generators. Global and non-local manage variable scope, and pass is a placeholder for empty code blocks. 3. Exception and module keywords. This group manages error handling, try, except, finally, raise, and assert. Import, from, and as are used to bring in code from other modules, which we'll cover next. And with may be used for resource management, typically with files. 4. Special keywords. Finally, true and false are the Boolean values and none represents the absence of a value. The keyword del is used to delete references to objects. To summarize, we've learned some of keywords, from simple flow control to advanced functional features like Lambda and yield. Knowing these helps you can write code correctly and understand what Python is trying to do. This marks the end of section 13. The next section focuses on structuring and organizing your code into reusable files using modules. We will learn how to import existing libraries and even our own Python files. Join me in Section 14 and our next lecture 14.01. Introduction. See you there.